All right, and so now we are ready for getting into a couple of examples to see how the derivatives of these inverse trig functions will become in action. Okay, so here we go. Let's look into our example 1. And just as usual, example 1 here is simply about, and pretty much any of our example here is about finding the derivative of a given function. So let's find f prime of x, or in equation notation, dy dx. Okay, and so our first function here in example 1, so now I'm going to call that part A right here, and the function here is going to be, how about y equals what I have here is in parentheses x squared minus 3x, and multiply with in product with sine inverse of x. Okay. All right. So what to notice here before we actually head into the problem is that there is a product. So what I see now is that our function here, our overall function, has comes out as a product of two separate factors. So you can think of that as a p of x, some function p of x, and the other one here is some q of x. Okay, and so now as I emphasize that what you're seeing here, what we're seeing here, what I'm seeing here is a product. So be ready for applying the product rule here. So again, we've learned in this specific lesson about how to find derivative of an inverse trig function, but that kind, so just like the exponential function or the trig function or the logarithm function, the same here. This rule that we've learned within this video lesson is a rule that only specifically meant for the inverse trig function family. Okay, but any of those rules, like the product rule, the quotient rule, and any of those other basic rules, including the chain rules later on, will all be, always be able to combine and blend it in any of these work here. So start being aware, raising your awareness about anywhere that you can use those product rule, quotient rule, and even the chain rules. They exist anywhere in our problem. Okay, and so now noticing that we have a product here, then I am going to start using my product rule. So dy dx. Okay, so right at start, dy dx, the product rule says we need to take the derivative of the first function among our factors here, among all of our factors in the product. So the first function, meaning I'm going to need to find the derivative of p prime. So for everyone being starter, I would recommend just writing down as a general setup for here. So we're going to take the prime, the derivative of our p of x, and multiply with the other function, keeping it the same. So that's why sine inverse of x remains here the same way it is. Okay, it's a superscript -1. And my writing board might be a little hard to make it clear. And now product rules say we need to add. Now I am going to multiply with x squared minus 3x, the p of x. I'm going to keep it the same, but now I'm going to need to multiply with with whatever comes out from as the derivative of sine inverse of x. Okay, so I'm going to need to take the derivative on sine inverse of x. Okay, so that's a starting setup point for us to get ready into the work. And so now in the actual step, so dy dx here, okay, as a further step, now taking this derivative is giving me the derivative of x squared minus 3x. At this point, anyone learning and following along with my lessons should be fluent with that. It simply now gives me 2x for the first term and minus 3 for the next term. And we're going to keep the product rule say we need to multiply with the other function, so but without the derivative. So I'm going to leave the sine inverse of x here. And then in my next step, I'm going to add. Okay, it's not really the next step. I'm only halfway of this current step right there. But so after that, this is p prime times q. And so now I'm going to need to add with x squared, the product of x squared minus 3x. So notice this time I'm keeping p of x the same, and I need to multiply with the derivative of our q function right here. So q is sine inverse. So now we're going to have to take the derivative of q. So sine inverse, and that's the whole point of learning about the derivative, how to find the derivative of this particular function right here. So sine inverse gives me 1 over square root of 1 minus x squared. Okay, so all that fraction that we have produced here is the derivative of this sine inverse function. And so for a problem like this, basically my main aim is for viewers or for anyone studying with me to understand how we can operate and apply our rules on inverse trig functions together with all the rules, the universal rules we have previously learned. But I'm not going to intend for users or for viewers or for any of my students to simplify any further. But be aware about your own skill how to simplify. But here for this example, I am going to finish right there at that. Okay, and that's so at this point we are done finding our derivative. All right. So I am going to take some time erasing the board, and let's look at another problem in our example 1. All right, so let's now call that part B of example 1, and give me a minute to quickly look into the problem bank that I have prepared. Okay, so what about the problem we have here is, so how about y equals, all right, 5 sine of x plus 4 cosine of x, and then being in product with tangent inverse of x. Okay, so 5 sine of x plus 4 times cosine of x. 2 trig functions being inside of our parentheses here, and then that's all of that. There is one function, and then we are multiplying with another function here, tangent inverse of x. Okay, so here once again what I notice, we have a product. So I can name this part here being some u of x. Okay, I purposely use different function names out there so that people can just get a generality of the product rule here. And here is some v of x, and now we have a product. So our function y here is a product of these two little functions. Okay, and so again, as soon as we notice we have a product here, then the product rule is once again going to be used. It's just the function is getting a little longer, that's all. Each one of our factor here in this product is getting a little bigger. That's all it needs. That's all it is. Okay, so now dy dx, once again, the product rule says I need to find, so in this case it needs to be u prime times v plus u times v prime. So now u prime, or it's always best to start out writing the exact function u right there, 5 sine of x times cosine x, but we need to eventually take the prime. And then from where that prime is, I am going to multiply with the other function. So this is v of x right here, tangent inverse of x. So that's u prime times v plus, and now I'm running a little short of space here, so I'm going to write it in my next line down below right here. But the later part of our product rule says we need to add with the product of, this is 5 sine of x plus 4 cosine of x. This is u without prime, but multiply with the derivative. So v prime comes along right here. I need to now find the derivative of tangent inverse of x. So I'm taking the prime of tangent inverse. Okay. All right, so that's the starting setup for us. Let me now navigate to the other board so that we can continue further into the problem. And so now into the next step. So dy dx is going to be, so one more time, I'm looking back at the earlier screen right there. But so this is our u, and we need to take u prime. So our function u has two terms, and they're all trig functions. The first one is a coefficient 5 with sine of x. The next one here is a coefficient 4 with cosine of x. So taking the derivative here, it can just simply go term by term. The sum and the difference rule also applied here. So that means into my next step now, u prime becomes, or u prime comes out to be, first term is a 5 times cosine of x, because the derivative of sine of x is cosine of x. And then the next term is 4, but the derivative of cosine becomes a minus sine. And that's the reason why now the terms, the sign between the two terms here switch. It was a plus sign earlier in the previous step before we took the derivative, but now taking the derivative, it becomes minus. So that's the derivative of u, or this is u prime. And now we need to multiply with tangent inverse of x being kept the same. Okay. And now product rule says, and so this is only halfway of our product rule. So to continue further, I need to add according to what the product rule says. Now I'm going to keep my original u of x the same. So 5 sine of x plus 4 cosine of x. It's all here, so this is u of x. But now I am going to multiply one more flashback into what we've seen in the earlier step. But see, this is u of x, and this is v prime. And so for v prime here, v itself is a tangent inverse. So now I'm about to take the derivative of tangent inverse. But that is just the entire reason why we've been learning a little bit, some basic understanding of how we took derivative of these basic inverse trig functions. So the derivative of tangent inverse simply comes out to be positive 1 over 1 plus x squared. That's the derivative of tangent inverse. And so once again, this is where I call it the end of our problem, part B of our example 1. Now again, I am not going to ask, I'm leaving that for students or for viewers to simplify this expression on your own. For this particular example, when I'm showing here, I don't really require anyone to simplify the expression, because my main aim of these examples here is to understand again how the new rules we have learned about taking the derivative of inverse trig function can be blended, can be applied together, can be used together with all of those universal rules we've learned previously. Okay. And so now I am going to take another amount of time to clear out my board, and let's do some more examples. So now I am going to step into example 2, and we will be doing the same kind of work in example 2. We find the derivative of a given function, and so let's stay with the same instruction of example 2 right here. Okay, so let's look at our first problem in example 2 right here. So how about part A? Our function this time is given to be, how about tangent inverse of 3x. Okay, so tangent inverse of 3x. So before I'm heading into this problem right here, I have to make clear again that this function, in the way how I see it, there is a tangent inverse, and then the arguments, the input of tangent inverse, instead of being the ordinary x, now it's some 3x. And so my order, the order of how I wrote these things, hopefully point out a certain truth about this function. So in other words, what I recognize here is that in this entire function we're looking at, that we're about to find derivative, then there's the 3x here is some inside expression. And then all of the tangent here is going to be, the tangent here is the outside expression. Okay, so that's a quick thing to point out right there. So let's formulate the idea. So the way how I see that now is that, and like I have already mentioned in some of the earlier lesson as well, that choosing an inside, there has never been a right or wrong inside, but in this particular problem, you can trust in my own experience of doing this. I highly recommend taking the 3x as the inside. Okay, so for the inside, we can think of that as a big variable u to substitute for 3x. And I introduced all this idea back in the days we specifically learned about how to use the chain rule. And so we can just take any expression and substitute that for a variable. And we call that for now the inside. And the whole idea about inside and outside is that once you have substituted away some expression, then whatever else remains after we have completely substituted away this expression. So let's have a look now. See, what we have now is y equals, after we took away, after we substituted away the 3x here, then your overall function now becomes a tangent inverse, but of u. So if you need to review my chain rule video lesson, then so do it. But see, that's how I call that. This is the outside and this is the inside. And so now, realizing that we have the chain rule waiting ahead for us here because our function is in the form that some little function is being inside of some other function. And so now, in that way, when we get into finding the derivative, the dy dx, chain rule says we first need to take the derivative of the outside. So the outside, now the derivative of the outside, but the outside function appears to be an inverse tangent. So we just now learned, just earlier in this video lecture right here, this lesson we're learning is 1 over u squared. Okay, that's the derivative of the outside. And of course, don't worry for now, because right now I'm using the temporary variable u right here, but later on we're going to put it all back together. Okay, and we need to multiply with the derivative of the inside. The derivative of the inside is this, u equals 3x. So the derivative of that 3x, okay, multiply with the derivative of the inside. And so now let's put it all together. U itself is substituted for 3x. It's a substitution for 3x. So our final answer here is going to look as following. 1 over 1 plus, it's a 3x, but in all square, because recall again that u is a substitution for 3x. And now multiply with the derivative of 3x. At this point, anyone viewing my video here should be fluent with this. Taking the derivative of 3x simply gives me 3. And now with something like this, we can put it in one fraction. So my final answer for this is going to be so our final dy dx here, dy dx is going to be 3 over, because we're just simply putting the entire fractions all together, all the little components into one fraction. So 1 over, now 3x in parentheses square will really become 9x squared. And that is how we are done with our derivative of this function. It was our beginning function was tangent inverse of 3x, and now we have found its derivative being 3 over 1 plus 9x squared. Okay, so now again I am going to take some time to erase my board, and we're going to look into another example problem. All right, so part B of the example. So let me now quickly look at another problem that we're looking at here. All right, so how about y equals 7 times sine inverse of x to the 4th. Okay, so our function here, 7 times sine inverse of x to the 4th. And so this problem, again, just like the earlier example, how I see it here, what I see here is that we are going to have an inside function. Because, and like I said, really there are no right or wrong inside function to be chosen, but here I highly recommend choosing this particular part like that, the x to the fourth inside of our inverse sine function to be the inside function. Okay, so now a big U can be x to the fourth, and once we substituted away the x to the fourth, then that's everything else remains in terms of the new variable is regarded as the outside function. So now our outside function appears as following: y equals 7 sine inverse of u. Okay, and so now once we clearly, and hopefully any viewers is going to agree with my recommendation about substituting, but if you chose to do something else otherwise, you have your own time, you have your own freedom as well to try out a different solution. Okay, and so now dy dx, be ready for the chain rule. So the chain rule says anytime we recognize there's an inside function and there's a function being inside of another function, then the chain rule is going to be used here, is going to be applied here. And so chain rule says we take the derivative of the outside. The outside is a sine inverse function over that big variable u, and we have a coefficient 7. So putting it all together, the derivative of the outside is 7 over, we just now learned in the earlier part of our video lesson here about how to find the derivative of our sine inverse. And so 7 over square root is a positive square root of 1 minus u squared. And for now, ladies and gentlemen, allow me again to use the outside variable, the big variable, because that's the variable that has something else in there. Okay, that's the variable that substituted the x to the fourth away. And then now chain rule says we have to multiply with the derivative of the inside. And the inside here, look right at that u. U substituted for x to the fourth. So that means now I'm going to take the derivative of x to the fourth. So taking the derivative of x to the fourth, so now 7 first term over square root of 1 minus. Now u squared is the same as x to the fourth all square, because u itself is already an x to the fourth power. Okay, I'm going to have to rewrite it. So x to the fourth all square. And then now that's the derivative of the outside. Now we need to multiply with the derivative of x to the fourth, which was the inside here. And so that gives me 4x cubed. All right. And so now the next step is to put everything here together in one fraction. Okay, so I'm going to once again navigate over to my other board, take some time to erase it, and then here we go. So the final answer as one fraction, as one rational expression. Okay, so 7 times 4x cubed is going to give me 28x cubed in my numerator, and in my denominator, square root of 1 minus. But be cautious here, x to the fourth all square is the same as, this is a power of another power, power of a power. So that means it's x to the 4 times 2, and 4 times 2 is 8. So our final expression here is 1 minus x to the 8 being inside of that square root in our denominator. Ladies and gentlemen, that is our final answer. And even if anybody is asking you, the viewers, my students, to simplify, this is all it can be simplified down to. So some problem comes out quite straightforward in the way of how it was already being simplified. Some other problems is a lot longer, but my entire intention of doing these problems is to give viewers and my students who studied with me a good hang of how to operate with these derivatives on the special inverse trig functions together with the other rules. But I'm not really aiming at having anyone to simplify any of those expressions here. All right, so now let's look at another problem in our current example 2. Now I'm gonna, before we end with this example 2 right here, I am going to use another one that's more challenging. All right, so what I have here is, how about part C? Our function y equals 6 times tangent inverse of 6 times sine of 4x. All right. 6 times tangent inverse of, and then there's a 6 times a sine of, sine but not sine inverse, sine of 4x. Okay, so now let's break it down a little bit term by term here. But how I see that now, first thing, I highly recommend that we can just take all that here inside of my big pair of parentheses, inside of my tangent inverse function as the inside, okay? So all that there 6 times sine of 4x, all that there being underlined with the red ink right here, all of that, let's regard it as the sine of x. I mean the inside function. And so just like that, same routine here, I am going to track down, nail down our inside function. So inside function in this case, I'm going to name that as an external variable u, a big U, to equal 6 sine of 4x. Okay, and now once we have substituted that, all that long, a little bit long expression 6 sine of 4x there with a variable u, then now let's look at everything else after we have substituted away that expression. So the entire problem now becomes, the entire function now becomes y equals 6 times tangent inverse of one big variable u. Okay, so one big variable u. And so that's clearly inside and outside. So now, but all it needs here is the patient to go through the problem step by step and watch out for things carefully, that's all. The function does admittedly look a little more, or maybe quite challenging compared to the earlier problems, and some viewers might start getting a little nervous about this, but all it takes is the patient. Okay, so right now I see inside and outside, and don't worry about these things, we'll get to that, okay? So there's inside, there's outside, so chain rule is going to kick in. So now I'm going to go with dy dx. Chain rule says we take the derivative of the outside function. So the outside function is quite simple. There's a coefficient 6, but it's tangent inverse of whatever that variable is, the u variable. So there it goes. So now I'm going to put that as 6 times the tangent inverse. Here gives me 1 over 1 plus u squared. Let's just leave it like that for now. And now I need to multiply with the derivative of, so the plan now is I need to take the derivative of, so let's write it down, all that 6 times sine of 4x right here. Now we need to take the derivative of that, because that's what the chain rule says. The chain rule says we take the derivative of the outside and then multiply with the derivative of the inside. Okay, let's take a pause right there for now. I am going to, instead of rushing into the next step, I'm just going to produce another little steps between by just simply cleaning out the terms here a little bit, kind of put it in a more clean up version. So 6 multiplied with this all of that fraction is going to give me 6 over, but now I'm also going to just put back that, put that 6 sine of 4x to substitute back into that u variable here. So now what I'm looking at is the first part here, the derivative of the outside. Now it's going to look as following. 6 over 1 plus, now all that 6 times sine of 4x, okay, being raised to the square power. Okay, that's not my final derivative. Now we need to take the derivative and multiply with the derivative of 6 sine of 4x. I'm a little narrow in space right here, so allow me to rewrite all of that. So hopefully I can squeeze my writing in a little bit. 6 all over 1 plus, in parentheses, 6 sine of 4x. Okay, all that square. That took care of our derivative of the outside. also substituted back that's the meaning of that u variable. Now I need to multiply. Now 6 times derivative, the derivative of 6 times sine of 4x. Okay, so now we have another derivative to take care. All right, and so now as we have gotten to this point, what matters next is just to find the derivative of this thing that I'm putting in the red box right now. Okay, so maybe a little bit of scratch work right here. I'm going to take some more time to erase my board, my other board. And let's now look over to the other board. And so now, just a little bit of scratch work, but 6 times sine of 4x. And now we're about to take the derivative. I'm just focusing right on that part because this part was the inside of our earlier problem, of our earlier step that we haven't gotten to. But now, well, let's look again. Here we have a 4x right there. Okay, and I highly recommend use that as the inside expression. So I have another sort of like a sub-level inside expression. So now in this, on behalf of this particular one right here, then inside can be regarded as some big z variable. Okay, so this is a 4x, and then our outside for this particular one, the outside here, okay, I'm really going in really small step by step right here, but it's 6 sine of the variable z, because all that 4x is being substituted by the big Z. And now we're gonna, taking this derivative gives me another chain rule work must be used here. All right, so derivative of the outside, but outside is a sine function. So derivative of sine is, by the way, that coefficient stays the same. Now it's cosine of z. Okay, cosine of z, that's the derivative of the outside on this particular little work. And now I need to multiply with the derivative of the inside, sort of like a dz dx. Okay, or the prime of that. So really it's 6 times cosine of z is a substitution for 4x, and then the derivative of 4x is just simply 4. So now I'm ready to put this piece, ladies and gentlemen, is a substitution for all that derivative work where I'm putting in my red box here. All right, so now I'm going to rewrite that step in my next board there. So that little work here is sort of done. So from the earlier step, dy dx came to 6 over 1 plus, in parentheses or in brackets, 6 sine of 4x all square. Okay, and then multiply with, and I put that part in a big red box right there. So we were on our way to find the derivative of that inside function, and that the derivative of that inside function is now here. Okay, and so in that way we're ready for putting all that work together. It's now 6 over, now the first part in our product here, 6 over 1 plus. Now I'm really getting tired of using too much parentheses here, so 6 sine of 4x, but square here, so it's going to give me the first factor here becomes a 36, and now there's another convenient way of writing sine. It's a sine square of 4x. Okay, that's one way we can write it, and then multiply, and so all that here now can be substituted by this answer. And really, I can now also multiply these two coefficients together, the 6 and the 4. So my overall answer here is multiply with 24 cosine of 4x. Okay, and so, and our final answer can come out easily to be, and one more little step through here. Okay, I'm a little narrow in space right here, so how about let me get back to the other board right there. right, so all together, now my final derivative there, 6 times 24 is going to be 144. Now we're looking at 144 cosine of 4x. Okay, that all of that goes into the numerator of our fraction, and then all over 1 plus, and all of this is in the denominator. 36 sine square of 4x. And that's how we're done. And this is quite simplified, so there's no other need to simplify any further. And besides, my main intention for these problems, again, is not to aim at simplification any longer, but I'm aiming at for viewers, for my students who study with me, to understand that even though we learn any specific rules about taking derivative for any specific family of functions, like say here we learn about the rules for taking derivative of inverse trig functions, but any of those specific rules here can always be applied together with any of those universal rules that we have learned previously, the earlier part of our days studying about calculus. Okay, so this is about the last example problem that I would like to introduce. Okay, and so that's all for us here in this particular lesson about derivatives of inverse trig functions.